All right, good morning, everyone. Welcome back to class. It's the 24th of September. So that's the wrong calendar. Here we go. So we're going to try to finish off chapter 3 today. We might not get it all done, um, but we'll get most of it done. And then on Thursday, we'll finish it up. And then we'll review, depending on how much time we have, we'll do a review on Thursday for the exam that starts next week, right? So exam 2 will open on Monday, and you'll have 3 days for that. Just like the first exam, you'll have to take it at a testing center, so it's proctored. You can have the same kind of formula card as before, front and back, one page, calculator, basically identical testing conditions. I think there's about, if I remember correctly, about 12 or 13 problems. So plan on about 12 to 15 problems or so for that exam, and it'll cover just chapter 3. Okay, so that's what's coming up. Do you guys have any questions? Anything you want to go over from the homework? Anything we've been talking about at all that you're wondering about? Or shall we just get going here with the new material? Nothing? Okay, well, what were we doing? We were uh, getting everything put together for confidence intervals. We understand how they work. We know what they're doing. We've even seen the formulas. But we haven't created our own confidence interval yet. And that's where we're at. We're basically ready now to create our own confidence intervals. Okay, so let's see, I got a question in the chat. Yes, you should be able to schedule that exam already. Can anybody confirm that? Has anybody scheduled their exam yet? Um, I'm like 90% sure, 99% sure you can schedule that exam right now, as well as any of the exams. Any of the midterms plus the final should be open for scheduling. So, but then again, I don't have to schedule myself. So if one of you could confirm, that would be great. Um, okay, so so let's look at this example here. We're looking at high school seniors, and we're wondering about the study abroad program in college. Okay, so the study abroad program, uh, so the way it works is during college, you take maybe a semester, or some people might take a whole year, and they go and study at a college or university in another country, right? And so, some people do this. I knew a couple people when I was in college, they did this. Most of the people I knew didn't do it, but it can be a good experience for sure. And so what they're trying to do here is figure out the proportion of all high school seniors, at least the ones who took the SAT, who believe they'll participate in one of these programs. Okay, so why would you care? Well, if you are an administrator at a university, you have to make plans for the incoming class, right? You need to know basically what they're interested in. And so, if you have lots of students who want to do this, then you probably need to, plan for that and have enough slots for the interested students. Okay, so that's the idea. They're trying to make a plan for the future. So they want to create a 95% confidence interval for the proportion who are interested in this study abroad program. Not just interested, but are pretty sure they're going to do it. Right? So so I always begin with thinking about what kind of data this is. So either a student is fairly certain or they're not. So it is categorical. And we know that when we're working with categorical data, the parameter of interest is P. So P is the proportion of all high school seniors who take the SAT, who want to do the study abroad while they're in college. Okay, all right. So since it's a proportion, I can actually give you 100% confidence interval. I know it's got to be at least 0 and at most 1, right? So that's actually 100% confidence interval, but it's such a broad interval that it's useless, right? Everybody knows it's got to be between 0 and 1. So So it's 100% confident, but it's 100% useless, right? Because it's so broad. So who knows what it is, right? Maybe it's about 50%, right? So maybe P is here, but we don't know exactly where it's at because there are millions of graduate, I believe, probably millions of high school seniors, right? And you can't talk to all of them and ask them about their plans. So we don't know what P is. So what we do is we take a sample and we calculate P hat. Okay. And then the idea is because of sampling error, P hat will miss P. So P hat is the point estimate. It's the one number that best estimates P, but it's a little bit frustrating because it's almost certainly a little bit off because of sampling error. So to make up for it, what we do is we build a margin of error on the right. Okay, so we go out a certain distance from P hat on the right, and then we go out a certain distance from P hat on the left. And with some, if we're lucky, then we actually do capture the parameter P. So we have a range of plausible values for P. Okay, and if you're following the polling for, the elections that are coming up, then you're basically looking at confidence intervals. Okay, so when you read the results of a poll, they always tell you P hat, and then they report a margin of error, right? And then you decide based on that margin of error how the candidate is doing, right? Okay, so what is P hat here? Well, they took a sample, right? And so the sample size was 1,509 and 830 said yes. So that is the number of successes, right? So let's put that down here. So 1509, and then we divide those two and we get about 55%. So go 830 divided by 1509. Okay. All right. Now, before we can use the formulas, we have to make sure that the conditions have been met. Okay. If you don't make sure these conditions are met, then you're taking a big risk, right? You're making a big gamble, basically. The formulas are based on a distribution, the normal distribution, and the normal distribution is based on certain assumptions. Okay, and these are basically the assumptions. So we have to make sure we have a random sample or a randomized experiment. Okay, so we look back at the problem and we look for evidence that it was a random sample. Okay, it says it's a survey, so that kind of indicates that it's, well, it is a sample. Doesn't really say that it's random, and then it also says they completed an optional web survey. Okay, so um, so it's a little bit murky here to me. I'm not completely sure that this is a great random sample, but on the other hand, collecting data is difficult, and sometimes you just sort of take what you can get your hands on. So here's what we'll do. We'll say we assume that it's a random sample. Okay. Now on the exam, I'm not going to be like, this isn't going to be a got you kind of question. I'm not trying to like trick people on this. So on the exam, here's what you should say. Unless it's very obviously not a random sample, then just go ahead and say, I assume that this is a random sample. Okay. Again, I'm not usually trying to trick people on this. I just want people to comment on these three and make sure they're at least doing what they can to check these requirements. Okay, so assume the random sample. Then are the observations independent? So what does independent mean? Well, you don't want this survey being done at just one high school, right? You don't want all the numbers coming from one high school in Davis County or something, right? Because people who go to the same high school are influencing each other. There certainly is a lot of differences there at a single high school, but still they have certain similarities and they're just not a great representative of the whole population, right? So part of the assumption in the normal model is that the sampled individuals are independent of each other. So how do we get that? Well, one way of getting independence is making sure your sample is small relative to the whole population. And that's what this inequality is saying. It's saying that your sample size, lowercase n, is less than 5% of the population size. So let's set that up over here. So, and you'll have to do this on the exam. You'll have to solve this inequality probably. So that's 1509 less than or equal to 0.05 n. Now, n, capital N, is the number of high school seniors who took the SAT. Who knows what that number is, right? So the next best thing we can do here is say, well, what would that minimum, or what would that population size have to be such that 1,509 is less than 5% of it? So we solve that inequality, dividing the sample size by 0.05, 30,180. So are there more than 30,000 high school seniors who are taking the SAT every year? Yeah, almost certainly. So we should be fine there. Okay, so then we have to make sure for independence to work, the sample has to be small relative to the population. But in step 3, we also want to make sure the sample isn't too small, right? So, if you only sample 3 students, that's not really enough, right? So we have to make sure it's large enough, and we have to make sure we have some of each. So we have to have some in both categories. If you sample 100 students and they're all in the yes category or the no category, then you don't really get much of a way of estimating p, right? So the rule of thumb is we need to have at least 10 failures and at least 10 successes. That's what these two inequalities are saying here. Okay, so we need to check for that. So we'll go np hat. Now, there's a fast way and a slow way of doing this. Here's the slow way. The slow way is to take 1509 times p hat, which is 0.55, and calculating that value. There's nothing wrong with that. It's what the formula says after all. But what does that number look like to you? 829.95. Isn't that just 830? Yeah, why isn't it exactly 830? Because of rounding. Okay, so 830, that's simply the number of people in the success category, right? So you don't even need to calculate that number sometimes, because if you know how many successes there are, you can just say, well, there's this, more than 10 successes. Well, what about the other one? Well, same thing with the other one. We can go quickly or slowly through this. Let's go slowly first. So we would have 1509 times 1 minus 0.55. We have to make sure that's at least 10. So there will be, we need to make sure we have at least 10 in the other category. Okay, so that times 1 minus 0.55. So 679.05. We also have 10 there, right? So there's 10 in both categories. Now, how could I have done that more quickly? Well, if there's 1,509 people in the whole sample and 830 are in the yes category, how many are in the no category? 679, right? So notice, I could have gotten that same number by doing a simple subtraction instead of a subtraction followed by a multiplication. Okay, so you can do that step more quickly or more slowly, depending on what you like there. So what have we done? We've shown that all of the conditions are met to be able to use the normal distribution. Okay, so we're good. So how does that work? Well, now we go to the formula. Okay, so there's a formula for it, and it's right here. Okay, you don't need to memorize it. It's here on your formula card. So this is in the second box down here. So the inference for one categorical variable. Right? So categorical variable P, typically, right? So we're doing inference about P for one population. And here's our formula. So what does that look like? It's the point estimate plus or minus a margin of error. So our point estimate is p hat. That's the one single best number to estimate p. So in our example here, it's 55%. So we would, if you have to guess what p is, the best guess is 55%, even though we know it's probably a little bit off, right? Okay. So let's think about this margin of error. So p hat is easy. We've been doing that for a while. Margin of error a little bit newer. In fact, we haven't used it yet. This formula, it's a well, we kind of have it. It's a z star, right? So it's a critical z-score times square root p hat 1 minus p hat. What is that? That's actually the standard error of p hat, right? We've seen that formula before, right? Up here, we saw that formula up here. We're substituting p hat in for p because we don't know what p is, right? But it's basically the standard error of p hat. So it's a critical z-score times a standard error. So it's telling us how many standard errors or how many standard deviations we need to go out in order to be, to have a certain level of confidence we're going to capture our parameter p. Okay, so let me add in just a little more discussion here on this. If you're interested in where this formula comes from, let me just, in about 2 minutes, try to give you a little more insight into that formula. So with our M&M's example, right, we were looking at the M&M's factory, and we basically showed that the sampling distribution for p hat is approximately normal. The mean, the middle, is p. It's the population proportion, right? The standard error for p hat, you could think of it as like how much p hat bounces around from sample to sample, is given by the expression 1 minus p times 1 minus p over n. This is all from previous discussions, right? Okay, so here's the idea. If I start in the middle of the distribution around p, and I go out, let's say 2 standard deviations from p, how much of the distribution will I cover roughly? So if I go out 2 standard deviations, what does the 68, 95, 99.7 rule tell us? If I'm going out 2 standard deviations in both directions, then won't I capture about 95% of the p hats? Okay, so if I go plus or minus 2 standard deviations, then I'll capture about 95% of the population. Okay, and the population here is p hats. So what if I turn that around? Okay, so here, let's say we have a p hat over here, right? So if I put a margin of error of 2 standard deviations on both sides of p, then I'll capture about 95% of the p hats. So here's the clever idea. Okay, the clever idea is, instead of putting those error bars around p, take the error bars and put them around p hat. Okay, so I'm going to take this error bar and I'm going to move it so that it's around p hat. Okay, so if I erase the error bar around p and I attach it to p hat, do you see how it's now over here? Okay, so let's see if I can erase that. Okay, then we'll do the same on the left side, on the right side. So here's p. I have a margin of error out to here. Well, if instead of putting that on p, if I attach it to p hat, I get the confidence interval. Okay, so the idea is, okay, if you take those margins, the 2 margins of error, right, and you attach them to p, then you're going to capture 95% of p hats. Well, that works in reverse. If you take the same margin of error and attach to both sides of p hat, then 95% of the time you'll capture p, right? Does that make sense? So that's where the formula comes from. If you want to be 95% confident, you go out about 2 standard deviations. And so it's 2 times the standard deviation. Okay. What if you want to be more confident? then you simply make this a larger value. If you want to be less confident, you make it a smaller value. Okay, so we have a table over here that tells you the values for the critical z-scores. Okay, it's right here. So if you want to be 95% confident, you go out, well, I was saying 2, but that's a slight approximation. The actual exact value is 1.96, very close to 2, right? So if you want to be 95% confident, you go out 1.96. If you want to be 99% confident, you go out 2.58. If you want to be 90%, so etc., right? So depending on what level of confidence you want, you use this critical z-score value. Okay, so these are the common critical values that we'll see. So I will, so you'll want to have this formula card on the exam, right? So here's that same table right here. So on the exam, when I ask you to calculate a confidence interval, you'll run over here to this table, you'll find your critical z-score, and then you plug it into your formula. Okay, so let's actually do it. Okay, so now that we've had a quick discussion of where that formula comes from, based on discussions we've been having for the last couple of class periods, let's use it. So what kind of confidence interval do we want to have here? We want to have a 95% confidence interval. Okay, so if we want to be 95% confident, let's pull our formula down over here. In fact, I'll just take it to the other document here. So I'm moving this formula to the other page, so I have plenty of room here. So if we want to be 95% confident, we're going to go p hat plus or minus, then we have our z star square root p hat 1 minus p hat over n. Okay, so 95% confidence means we go out 2 standard deviations. Well, actually, more precisely, 1.96. Okay, how do I know that? It's on my table. Okay, so what was p hat? Well, we calculated that to be 55%, right? In our sample, it was 55%. Okay, so then we go 1.96. Okay, and then we put in our p hat again, 0.55, 1 minus 0.55. And then we divide that by the sample size, which was 1,509. A common mistake students make is they do something like this instead. Instead of putting the radical over the entire thing, they'll just put the radical in the numerator. That's wrong. Okay, so don't write that down. That's what you don't want to do. What you do want to do is calculate this inside part first and then take the square root of the whole thing. So notice that 1509 is incorporated first before you take the square root. Okay, very easy to make that mistake, and then the margin of error is way off. So this point is calculator work. Okay, so we just have to follow the steps here on the calculator and it should be fine. Okay, so I always work from the inside out. So I have 0.55 times 1 minus 0.55. And then we divide by 1509. Okay, so that's this inside piece. I'm going to take the square root of that now. Okay. Notice that I haven't cleared out my calculator at all. The students will sometimes have a feeling like they need to kind of start over and like round a number. But if you leave the digits there in your calculator, you won't have as much rounding going on, and we don't really like to do rounding until the very end if possible. But that said, it is easy to hit the wrong button on your calculator and then you have to go all the way back to the beginning. So I do like to have kind of these intermediate steps where I'll write out some of the numbers with lots of extra decimal places, just in case I key in the wrong number and I don't want to start over all the way from scratch. Okay, so it's like a crumb trail here that I'm leaving. Okay, so then we're going to go times 1.96. Okay, so what is that quantity there in the calculator? That's the margin of error. Okay, so then 0.025101. So what is that? That's our point estimate. That's the middle of the interval. And that's the margin of error. That's how far out we're going to go on both sides. So that's about 3%. So our margin of error will be centered at 55%, and then we'll go out about 3% out to about 58% on the right and down to about 52% on the left. So we're 95% confident that the percentage of high school seniors who took the SAT and are pretty certain they're going to do study abroad is somewhere between about 52% and 58%. Okay, and so in this case, that allows administrators to make plans for their study abroad program, right, at their university or college, right? So they can plan, this is how many slots we need for that program to work. That way, they don't have to make big changes at the last minute. Okay, so let's finish that up. So let's see here. So we're going to go plus 0.55. So go plus 0.55. So that's going to be 0.5751. And then if I also go 0.55 minus that value, okay, so there's my margin of error. Now I'm going to make it negative and add it to 0.55. So in other words, I'm subtracting it from 0.55. I'm going to get the left end point 0.52. What would that be? 549. Yeah, 49 to the fourth decimal place. There's not really a golden rule about rounding. So just, do what makes sense in the context, and especially in a class, do what the directions say, right? So, okay, question. I keep getting a different number on my calculator for the first part. Okay, so you mean for this 0.5751, Armand? Which part exactly do you start getting a different number on? Do you mean the margin of error up here? Okay, let's see. So yeah, let's do that part again. So that what you've written there is the inside part of the standard deviation expression, right? So let's do that together first. So let's see, it's going to be 0.55 times 1 minus 0.55. Okay, then you can hit equals if you want, and then divide that by 1509. So is that what you got, or you got something different? Maybe yours looks different because of this e negative 4. So feel free to tell me. Just you can open your mic up if you want. But my guess is maybe you're not getting this e negative 4 on there. So let me just tell you what that e negative 4 is. So that's my calculator is saying 1.64. I'll just go to the fourth decimal place. And then at the end, it says e negative 4. Okay, so probably some of you know what that e negative 4 means. This is called scientific notation, and it's a way of expressing, it's an easier way of expressing very large or very small numbers. And what it says is, okay, take this number and then move the decimal place a certain number of times. So if it's a negative 4, we're going to move it 4 places to the left to make it a smaller number. 1, 2, 3, 4. Okay, so that's going to be 0.00016,402. Okay, so that's this value right there. Okay, let's see here. So Julia asked me a question. I keep getting 0 when I do the top part. You mean you keep getting something like 0.000? That's kind of one of the reasons we don't want to round too soon. Is this helping Armand and Julia? Oh, you figured it out? Okay. So is it making sense, Armand? Then we're going to take the square root of that. Okay. And then, so that's this number right here. And then we need to multiply that. So this number in my calculator currently is the standard error for p hat. and then we need to multiply it by the critical z-score. So we go times 1.96, and we have it 0.0251. Everybody feeling okay about that? So let's try to visualize this. Again, I'm 100% confident P is somewhere between 0 and 1, but that's such a wide interval, it's useless. So we go P, P's in there somewhere, right? P hat is right here. We actually know P hat, that comes from our sample, it's 0.55, right? Now, so for a lot of people, that's good enough, right? 55%, and then we know P is pretty close to 55%. So depending on, how interested you are in stats, that might be good enough. But a lot of people take it further, right, and use the idea of the margin of error or the confidence interval. So we're going to attach a margin of error on the right and a margin of error on the left that creates an interval of values, and we're 95% confident that it captures P. Okay, so that margin of error is 0.0251. So we added that and then we subtracted it, right? So on the right, we have 0.5751. On the left, we have 0.5249. So we've done it. We've actually calculated an interval here. So that's great, right? So let's interpret it. And for the interpretation, we can use that same three-part interpretation we've seen before. So how does it begin? We say we are 95% confident that the interval from, and you can do percentages or proportions here. So maybe I'll do 52% to maybe 58%. Okay, so we tell our audience how confident we are, and then we explain what the interval is, and then we say what it's trying to capture, right? So the interval from 52% to 58% captures the true proportion of, okay, and if you want to lose all of your points, you talk about the true proportion of people in the sample, okay? We don't need a confidence interval for p hat. We know what p hat is. Exactly, it's 0.55. We need the confidence interval for p. So it's the true proportion of all high school seniors who take the SAT who are fairly confident or fairly sure they will participate in a study abroad program in college. Okay. So very, very useful to administrators planning out, one of their important programs. I imagine that would be a pretty complex program to have in place. You have to get all sorts of agreements with other universities and traveling and everything. So not an easy thing to do, right? Any questions there about that? Okay, so I would like you to know how to do that by hand. But most of the time, I encourage you to use software to do this. Okay, so do this by hand a couple of times. Get it, kind of get that formula figured out and kind of work with that formula a few times by hand. But then after that, it's fine to just switch over to software to create the confidence interval. Okay, that's what actual practicing statisticians and data scientists do. They're not really going to do this by hand very much. They use software to calculate these, and you should too. So let me show you how to do this in GeoGebra. Okay, so we're all done with the problem, but let's just do it again, but in like 30 seconds, okay, using software. Okay, so we need the formulas. They tell us what's going on. They're that's how the theory works, right? And we need them so that we can build on this and have even more complex ideas in the future. But for getting for kind of speed purposes, we like to be able to use the software as well. So let's go over to the software here. So of course it's GeoGebra. So let's open up GeoGebra here. Okay, and then so we're going to hit the toggle, the three dots. We go to probability, no, not probability calculator, sorry. It's, yes, it is probability calculator. Okay, so we go to probability calculator, then we go to statistics. Okay, and then there's this drop-down menu. What is this? This is basically the list of all of our different confidence intervals and hypothesis tests we're going to do this semester. Okay, so it's kind of a long list, but pretty much, so we have chapter 3, chapter 4, chapter 5, and in each of those chapters, we're going to learn 2 or 3 of the inference methods on this list. So by the end of the semester, you'll know how to do pretty much all of the ones on this list. Okay, so we have to figure out a way of, determining the right inference procedure. Okay, so what are we doing here? Well, we have tests here. Tests, those are hypothesis tests. Okay, so we're building a confidence interval. Okay, so it's not any of these tests. What is a confidence interval? It's an estimation, right? We're estimating some parameter. So it's one of these estimates down here. Oops. So which one is it? Well, we're working with categorical data, which means it's a proportion. Okay, so we kind of narrowed it down here. It's either a z-estimate of a proportion or a z-estimate difference of proportions. Okay, well, we only have one population, so it's not a difference of proportions. We're looking at one proportion here. So we have a z-estimate of a proportion. Okay, so we go to z-estimate of a proportion, then we put in the confidence level. Well, it's 95%. Then we put in the number of successes. Then we put in the sample size. Okay, and notice down here, we have our answer, right? There's our confidence interval that we calculated by hand, 0.5249, 0.5751. It's right there. Now I've got in lots of decimal places of accuracy, but it's the same number. What else does it have? Down here at the bottom, it has that same interval, but in a different form, different format. It's p hat, the 0.55 point estimate, plus or minus the margin of error. So I like this bottom format quite a lot too, because it tells us what the point estimate is, the middle of the interval, and then it tells us the margin of error. So about the 3% margin of error there. Okay, so I'd like you to be able to do both. I'd like you to be able to use GeoGebra to do things quickly, but I would like you to do it by hand a few times so you get comfortable with the formulas and that way the theory can you can get more comfortable with the theory of confidence intervals as well. So let's do a couple more to get the hang of it, and then we'll talk about hypothesis testing, and then we'll be almost done here with chapter 3. Are there any questions about that problem before we move into the next one? Okay, so here we're looking at the results of a New York Times CBS poll that was done, and they were asking people about the Supreme Court. Okay, and so they looked for the percentage or the proportion of Americans who approve of the job the Supreme Court was doing. And this is an older poll. This was back in about 10, 12 years ago. And so if you read the results of the poll, they basically say, here's the confidence interval. So it looks like, between about 41 and 47% of Americans at that point were approving of the job that the Supreme Court is doing. Okay, so we know what the answer. So let's see how to get it. So let's kind of mark that out. Just kind of blur that out for a second and see if we can get the confidence interval. Okay, so what is the confidence interval here? Okay, so what we do is we say, well, p hat is the number of successes Okay, so the people in the category of interest, and then we divide that by 976. Okay, so 429 divided by 976. So about 44% in our sample were approving of the job that the Supreme Court was doing. Okay. All right. So what do we do with that? Well, I can give you 100% confidence interval. It's got to be between 0 and 1. Okay. So, but that's so wide that it's useless, right? So P is somewhere in there. And we have calculated P hat to be about 0.44. Because of sampling error, P hat misses P. So we're going to build a margin of error on the right and a margin of error on the left, creating a confidence interval that we hope captures P. Right? So we're very interested in understanding public opinion about various things. Just it helps society to probably helps society to run a little bit better if you have an idea of what's going on, right? So we have this confidence interval there. Let me make it more symmetric around P hat. P hat is always the middle of the interval. Okay. So we need the right endpoint, we need the left endpoint. It doesn't ask us to do this on this problem, but we probably should do it. And on the exam, you'll have to do this. We want to check that the conditions have been met. Okay, so what are the conditions? We need randomness. And by the way, these conditions are on your formula card. You don't need to memorize these. So we need to make sure we have a random sample. We need to have independent observations, and we have to have at least 10 successes and at least 10 failures. Okay, so do we have randomness? So we go to the question prompt, and we're looking for evidence that we have a random sample. So this is almost certainly a random sample. Why? This is a professional media organization, and if it were found out that they were using bad polling methodology, they would be like disgraced, basically. Okay, so these polling organizations, I mean, they're very careful about using accepted scientific procedures. Okay, so we can safely assume that this is a random sample. Let's see. So yep. So it says poll, and so I'm going to go ahead and assume that this is a random sample. So again, I'll say assume random sample. If you are interested in polling, I encourage you when you read the results of a poll, they'll often have like a hyperlink where you can explore further the results, and they'll talk all about the methodology, and they'll talk more about the randomness of it. And sometimes you'll see that they were using like a stratified random sample, okay, so or other kinds of sampling methods. It's really interesting to read those explanations. Two, we have to make sure we have independence. So that means the sample is small relative to the population. Good rule of thumb is less than 5% of the whole population. So let's see, we had 976. Clearly, that's less than 5% of the whole population, right? So we divide through by the 0.05. So we're going to have 976 divided by 0.05. So 19,520. Are there more than 19,520 people in the US? Sure, right? So again, that just means that the 976 people in that poll are not really influencing each other, right? They're independent of each other. They're not all from the same town or the same like extended family network or something, right? I mean, they in other words, they just don't know each other. Okay. Third, we have to have at least 10 successes and at least 10 failures in both categories. So let's do this quickly. We know that there were 429 who said yes, they trust, right? Or they have confidence in, or they approve of the job, right? So that's more than 10. So if 429 said yes, how many said no? Well, there are 976 people in the sample minus 429. So 547 said no. We need at least 10 in both categories, and we have more than enough in both categories. So this sample is adequate for creating a valid confidence interval. By the way, what we'll see in today, actually, hopefully today, but definitely on Thursday if we don't today, that 976 is actually a perfectly good sample size, even for a very large population like everybody in the US, right? So there's like about 400 million people in this country, right? And it turns out you only need to talk to about 1,000 people to get a really good confidence interval. That might surprise you. So let's see. So where are we at? Well, we're ready to calculate the interval now. Okay, so the confidence level, we want 95% confidence. We put in 429 for the number of successes. We put in 976 for the sample size, and we hit go, right? It's as easy as that to get the actual interval. Understanding what the interval is, understanding the formulas, where they come from, making sure the assumptions are met, that takes a little more work. But actually getting the numbers right is very easy. So we go to the probability calculator, we go to the statistics panel, and then we come to this drop down. And I'm more than happy to go through this a couple times if you want. Then you have to figure out which procedure we're using. By the end of the semester, we'll have like 7 or 8 or 9 of these different procedures. For now, we're actually on the very first one. Okay, so what are we doing? We're not doing a test. We're doing an estimate. That's what confidence intervals do. They estimate a parameter. So which parameter are we estimating? Are we doing a mean or a proportion? Well, we haven't even talked about means really. So it's definitely not a mean. This is categorical data. Either somebody approves or they don't. So it is a proportion. And is it a difference of proportions? No, we just have one population that we're looking at here. So it's z estimate of a proportion. Okay, so we're going to put in the numbers here. So what was that, 429, then 976, and there we go. All right, there's our p hat, our midpoint there of 44%, and then we have our margin of error over here. So let's write that down, 0.0311, 0.0311. So it's telling us the margin of error, so 0.0311. So I'm going to add that to 0.44, and then I'm going to subtract it. I probably shouldn't use 0.44. We don't want to have as many rounding issues. So I'll go 0.4395 plus 0.0311. Okay, so that's 6, 7, so about 0.4706 on the right. Okay. Then on the left, we'll go 0.44, right, or 0.4395 minus the same margin of error, 0.0311 on the left. Okay, so that'll be 480.4084. Okay, so we have our endpoints there, and we're done. We have our confidence interval. So we can use the margin of error, adding and subtracting on both sides of p hat. Or do you see how it gives us the same numbers here as a lower limit and an upper limit? We like both. This is probably a little bit more direct, but then the interval form here is also nice because we know what the point estimate and the margins and the margin of error is. Okay, so we've got it. We've got the lower limit, got the upper limit, and we're good to go. So what is that? About 41% up to about 47%. Okay, so the confidence interval is going from about 0.41 up to about 0.47. Get that right? Yes. So we need to interpret that correctly. So how would we say that? We are 95% confident that the interval from, what did I say, 41 to 47? It's about 41% to 47%. Okay, so then you explain what the interval is. And then the last part is what you're trying to capture. Captures the true proportion of Americans who approve of the Supreme Court back in 2012, right? So it's probably different now, just because things kind of tend to change over time, right? So anyway, but sometimes we are interested in history, right? You're kind of looking back in time to make a comparison. So yeah, good. What do you guys think? So confidence intervals are indispensable for political scientists. They're using these all the time, at least the more quantitative political scientists. Economists use these for the same exact reason. So sociologists. So these are really commonly used in the social sciences and definitely the physical and medical sciences as well. Any questions there? So not too bad. I want you guys to try one, unless you have questions. This next one, it's a little bit kind of more of a funny example, but it's kind of fun to have fun sometimes. So we're looking at cell phones and going to the bathroom with your cell phone. Okay, so there was a survey that was done, and they talked to 1,000 adults, and they asked them if they bring their cell phone with them to the bathroom every time, and 241 said yes. So I want you to go through this. I want you to make sure the conditions have been met. Then I want you to calculate the confidence interval. And you can do that by hand or with GeoGebra, or do it both ways if you wish. Then interpret the interval, and then I think we'll be good here with confidence intervals. And what we'll do after that is our hypothesis test, and we'll be all done. Okay. So I'll go quiet for about 4 minutes on this and let you work on it. So we'll come back together at 12:28. Okay, so 12:28, let's come back here together. I will open up the breakout room if anybody wants to jump in there and talk with each other a little bit. Feel free to do that, or just work solo. What happens? Yeah, this is a great question, Brock. What happens if we can't assume the sample is a random sample? Okay, so there's two ways of asking this question. The first is, okay, if you're actually doing this in real life for your job, what do you do if you can't assume it's a random sample? Then secondly, the other question is, what do I do on a test, right? In this class, on my next exam, what do I do, right? So in both cases, what we would probably end up doing is we would go forward with the analysis, but we would put an asterisk next to it and say, we're not really sure this was a random sample. Okay, and so because we're not sure it's random, the results of this might be a little bit dodgy. Okay, but we also know that it's difficult to collect data, and it's still probably not completely useless for us to create a confidence interval. So usually what will happen is people will go forward with the interval, and they'll explain very transparently that the methodology is a little bit imperfect. Does that make sense, Brock? So I would encourage you on the exam to do the same thing. Just say, I'm not sure that this has been met. Okay. So just give your best opinion on that. Most of the time it will be a random sample. I usually try to say explicitly, hey, this is a random sample and the problem. But if it doesn't say that, then you can kind of choose what you think about it. But in either case, go ahead and go forward with the whole confidence interval calculation. Good. Okay. All right. I'm going to just go quiet here for just a minute and let you guys work on it. Okay, so what kind of variable do we have here? Is this categorical or quantitative? Anybody? Categorical. Okay, so everything we've done so far almost this semester has been categorical. Okay, but in chapter 4, that'll change. We'll get into quantitative. And then in chapter 5, we'll do both categorical and quantitative at the same time. So classifying it will become more complicated and kind of more necessary as time goes by this semester. So for now, it's all categorical pretty much. Then we check the requirements. So it says random. So on the exam, I don't just check things off. I want you to comment on it with words or equations. So just say something like says random. Okay, so it says random. Then we have to solve our inequality. Did anybody solve that? If we have 1,000 for our sample size, how large does the population have to be to make that sample less than 5%? Anybody get that? You will have to solve that on the exam. Great, it is 20,000. So as long as the population you're targeting is more than 20,000, 1,000 is fine. So even in a small town, say in Bountiful, Utah, uh, you can still ask 1,000 people and they probably don't know each other, even in, a small town like Bountiful. Okay, then we have to make sure we have enough successes and failures. So a success here is somebody who takes the phone with them every time to the bathroom, right? So it sounds a little bit funny, but how many is that? That's 241. That's more than 10. Okay, so if there's 241 successes, how many failures? Well, we just go 1,000 minus 241. 759. That's also more than 10. So everything is good here. We've got a good data set as far as we can tell anyway. And so we should be able to do valid inference about the whole population. So we get our interval. We can use the formulas or we can use software here. So let's do GeoGebra again. So we go to the toggle, the 3 dots. By the way, did anybody get it? Can anybody put their answer in the chat before we proceed here? So we go to statistics, and then we have to choose the right estimate. Okay, or choose the right procedure, right? So tests, well, those are the hypothesis tests. We're not doing a hypothesis test here. We're doing an estimate, and it must be an estimate of a proportion, right? So we go Z estimate of a proportion. Okay, then we put in the confidence level. Now we're changing it a little bit. Why would we want less confidence? Well, less confidence means one of two things. Either you have a smaller sample size, which means it's cheaper, right? Or you have a narrower interval, which is also kind of good because that means you get more precision, right? So, it just kind of comes down to, balancing the different parameters here. So sometimes we'll want 90, sometimes we'll want 99, okay? Sometimes, but usually 95 is kind of right. Okay, and then we put in the number of successes, which is 241, 1,000. There we go. Okay, so it's looking like from about 22% up to 26% are taking the phone with them every trip to the bathroom, or probably more accurately, that's the number of people who say they are, right? So it's probably higher than that, just because it's slightly funny topic to talk about, right? Okay, so construct a 90% confidence interval. So that's looking like, or did I do that right? I've got different numbers here. Did I do something wrong? No, that's right. That's right. Okay, everything's good. Okay, so we've got our interval. So we're looking at 0.2188 up to 0.2632. So that's the interval. What does it mean? Okay, well, it's got the same 3-part interpretation. Okay, we're 90% confident that the interval between 21.9% and 26.3% captures the true percentage of all Americans who bring their phone with them to the bathroom every time. Or that's the number, that's the percentage of people who would admit to it, right? Okay. And if we wanted to write that as a proportion, it's the same exact thing except as a proportion, right? So there we go. Let's see. Is P always greater than P hat on the number line? Nope. Nope. Sometimes P hat will be an underestimate. Sometimes it'll be an overestimate. Yep. I might have I might tend to draw it that way, but no, P hat can definitely be less than P. Yep, absolutely. About half of the time it will be less than P. The other half of the time, more than P, typically. Good question. What do you guys think about this? Not too bad? What else can we do with P hat? Well, the confidence interval is very useful. It gives us an estimate of P. But the other kind of inference that we like to do, and we commonly see throughout various industries and fields of study, we like to do hypothesis testing. Okay, so that was actually the first kind of inference we did this semester was the hypothesis test. So earlier, what we did is we used our applet. Okay, right? So basically flipping coins to see, what the p-value is, right? So we could decide if we wanted to reject or fail to reject. Well, that applet's great, but the other way we can proceed is by using the normal distribution. If p hat is normally distributed, then we can use the normal distribution to get a p hat. Okay, so let's talk about hypothesis testing for a little bit, and then we'll be almost all done here with this chapter. Okay, so this next example is perfectly good. So why don't we jump in and have a look at this? Okay, so diet soda, right? I think a lot of people would prefer drinking diet soda to regular soda to, as a healthier, option, right? But what's the problem? A lot of people don't really like the taste of it, right? They're used to regular soda, and then when they try diet soda, it just doesn't taste as good, so they don't drink it, right? So if you can find a formula that would, basically be so good as a diet soda that they couldn't tell the difference, then you would be very wealthy, right? Because a lot of people would buy that, right? Just so they would consume less sugar and stuff, right? So what we're doing here is we're thinking about a test taste. Okay, so at all these companies, they're developing these diet sodas, and so they're always bringing people in for test tasting to see how good their product is, right? So that's what we're thinking about here. A researcher wants to test the claim that some people can tell the difference between diet soda and regular soda in one sip. Think about that. Can you do that? If you had one sip of Diet Coke, could you tell it's Diet Coke? I think I probably could, but who knows? Maybe I need a little bit more. Sometimes, you need a couple drinks, right? But maybe, you're good enough on one sip, you can tell the difference. So how can we test that? Well, they had a random sample of 80 people, and then before they were tested, right, he filled 80 plain white cups with soda. Half of the cups were diet and half were regular, and they were randomly assigned. And then each person was assigned a cup, right? So you either have diet or you have regular in your cup. You don't know what it is. There's a number on your cup, right? So they can identify what kind it is, but you don't know what it is, right? So you take your sip and you say, okay, this is diet or this is regular, right? And so out of those 80, 53 correctly identified the soda in a single sip. So do these data provide strong evidence that more than 50%, that a majority of people who claim that they can tell the difference between diet and regular in one sip actually can? Okay, so how would this fit into hypothesis testing? Well, either you can or you can't, right? So in one sip, right? So in one sip, either you can or you can't tell the difference. So there's two categories, right? So it's categorical. So we know we're looking at P. And by the way, everything in this chapter pretty much is the proportion. So it's P. So just like before, we'll have H0 colon P, HA colon P. Then you all know that the null hypothesis is always the hypothesis of equality. So equals some value. Well, what value would it be? So let's look at the question. Do these data provide strong evidence that more than 50%, what is that? It's a majority, right? Can tell the difference. So sometimes it's easier to find the null and then determine the alternative. But here, I think it's more, it's clear that this is the alternative, right? More than 50 is more than 50. And we know that the alternative is always the hypothesis of a difference, right? Of some inequality. So if the alternative here is p greater than 0.5, then the null has to be p equals 0.5. So you guys will ace that part because you've practiced with that, right? That part is no different than the applet we've seen before, right? By the way, let's go ahead and use the applet. We're not using the applet in chapter 3, but just to kind of remind ourselves of the applet a little bit, how would that work? We have 53 out of 80, right? So we have a p hat here of 53 out of 80. Could tell the difference, right? So what is that? So we go 53 divided by 80, and it's about 66%. 66% is not 50%. It is indeed more than 50%. But is it so much more than 50% that we are convinced that this is an actual thing, not just some fluke due to sampling, right? Well, earlier in chapter 2, what we would do is we'd say, okay, no problem. We go to our applet here, and we flip a bunch of coins, or we have the software flip a bunch of coins for us, right? So we go to one proportion, we put in the null value, we put in 80 here, and then we start drawing samples, right? So draw samples, let's hide those coins, draw samples, draw samples, draw samples, right? Let's hide the coins for a little bit, right? And then we do that enough, and we start building up our null distribution. Okay, so let's do it more quickly, right? So 100, 100, now we're up to like 1,000, right? And then in their sample, they had 53 correctly identifying it, right? So if we put that boundary in, we see that we get a p-value of 0.001. That's pretty strong evidence against the null, right? You guys remember doing that? And then if you want to do like a ton of these, you can do 1,000, right? So the p-value does seem to converge there at about 0.0017, right? So we see our null distribution here looking much like a normal distribution, right? And then so with the old technique, we look at the proportion of the null that's as extreme or more extreme than the 53 that they got in their sample. In the new technique, we're not going to use this applet, but we are going to use the normal distribution, right? So we're basically just saying the null is a normal distribution. So let's do that. Okay, but before we can do that, we have to make sure the conditions have been met. Okay, so do we have a random sample? Yes, it says random. Right, these were randomly assigned. Everybody's randomly assigned to either get a diet or a regular. So we're good there. Then we have to make sure that the sample size is less than 5% of the whole population. So 80, is that less than 5% of all soda drinkers? For sure, right? So we divide by 0.05, 0.05. So 80 divided by 0.05, 1,600. So clearly, a random sample of 80 people, these 80 people are not going to know each other. They're not going to be, influencing each other in any way, right? Then we have to make sure we have at least 10 successes and 10 failures. Now this is more complicated than the other one. Notice that the formula is slightly different. When we were doing confidence intervals, we had p-hats here. Why don't we have p-hats again? Well, with the hypothesis test, we the whole logic, or part of the logic, is that we're assuming the null is true. Okay, so what we do here is we say, okay, let's assume that the null value, or this 50%, is true for p, right? So that's what that 0 there means. It's the null value of p. So we're assuming the null is true. If that's true, then how many successes are we expecting to get? So it's not as easy as with the confidence interval. With the confidence interval, you can simply count the number of successes, but here we have to use our formula. Okay, so we take n, which is 80, and we go times 0.5. Okay, so it's not 53. That's confidence intervals. This is different. It's going to be pretty close to 53, but a little bit different. Okay, so under the null, we're expecting about 40 successes. And then so we go n1 minus p0. So what is that? That's 80 times 1 minus 0.5. That's also 40%. That's also 40. Okay, so we're expecting about 40 successes and about 40 failures if the null is true, if there's no clear majority, right? So that's also been met. So since those three conditions have been met, we have a good reason to believe that the null distribution, this distribution here, will be normal. And we can kind of see that it is, right? I mean, that's pretty obviously, normally distributed. Okay, so if the null is true, what does the sampling distribution look like? Well, it looks like that graph we were just looking at, right? In our applet. Okay, so it's going to be a normal distribution. The mean will be in the middle. So we have a mean of 0.5. And then the sampling, the standard error will be that same formula we've seen several times now. It's going to be square root p 1 minus p over n. We've seen that formula many times now, right? So we go 0.5, 1 minus 0.5, and we divide that by sample size, which was 80. Okay, so we have 0.5 times 0.5. Then we divide that by 80. And we take the square root of that. So 0.0559. Okay. So p hat would be expected to bounce around by about 6% there. All right, so what sample values would be surprising? Well, what we do is we put in our p hat, right? So our p hat is over here. The p-value is the right tail of that distribution, right? So it's anything beyond that boundary, right? So the p-value would be over there beyond p hat. What sample values would be surprising? Well, any value where the associated p-value is less than the significance level. The significance level is alpha. Okay, so that's how it's going to proceed. We're going to find p hat, then we're going to find the proportion of the normal distribution that's beyond p hat, okay, and then that will be the p-value, okay, and then if that's less than alpha, we reject the null. That's the idea, okay? So how do we get our p-value? Well, we need our z-score, okay? So we calculate a z-score for our p hat, okay? So let's do that right here. So it's the same z-score as it's always been. It's an observed value minus the mean divided by the standard deviation. It's a little bit more complex looking, but that's what it boils down to. It's an observed value minus the mean divided by the standard deviation. So p hat, 0.6625 minus the null value 0.5, and then we divide by this expression, which we've already calculated to be 0.0559. Okay, so that works out to be a z-score of about 2.91. Okay, so what does that mean? It means if the null is true and that a majority of people can't tell the difference between diet and regular, then that's okay, but we got a p hat that has a z-score of almost 3 standard deviations away from the mean. How far out are you in the distribution when you're 3 standard deviations out? Well, you're in the very extreme tail of the distribution. Okay, so what I'm getting at here is we can probably reject the null. This p hat result is quite far away from 0.5, far enough so that we have good evidence against the null. Okay, so we got like 95% of the way through this problem, and then we ran out of time. I think it would probably be best if we paused it here, and then on Thursday we can just kind of come back and go through this problem more or less from the beginning. Never hurts to see things twice. If I keep you here just a little bit over time and to finish off this problem, we'll end up going pretty far over time today. So we'll just stop there. We'll kind of pause it, and then we'll just kind of go back through it. We'll rewind a little bit on Thursday and kind of start from the beginning. But we're almost there with everything in this for this chapter. Um, we just need to do a couple more hypothesis tests and then some sample size calculations, and then all done with chapter 3. So you're in a good spot here. You have a whole week before you have to take the exam, right? Today's the 24th, so in theory you could take it, as late as next Wednesday. So basically, by the time your exam rolls around, you'll have had a week to let all this digest. So I think you're in a good spot here. So yeah, try to get as much of the homework done as you can, and then on Thursday we'll finish up chapter 3. Are there any questions as we break here for today? Nothing? All right. Well, have a good one, guys, and see you on Thursday. Okay, thank you.